we have our last quiz. It's on classes 36 and 38 and 39. 37 was our test day, so 36, 38, and 39. So your projects are not officially due. This project here is not officially due until Monday. However, if you want to pass this in anytime before now and next Monday, so that I can grade it for you and you can have it back in time for your final, I'm willing to do that. So you can pass this in at any time. If you pass it in next Monday, I can only give it to you the day of your final, which is a week from Wednesday. So if you want to finish this up either Wednesday or Friday this week, I can get it back to you, and then you'll have it to review for your final. Okay? So it's up to you, whatever you want, depending on your other course load. You can use 4 sheets for your final exam. We'll talk about that more next week, okay? Or I don't know yet. I got to talk to Caitlin. They're supposed to be handwritten by you, but we can talk about it. Okay. So let's get us started off here, Coleman, with logarithmic functions. So today we're going to look at models for logs with using log equations. As you know, on Friday we looked at models using exponential functions. So today we're going to be looking at models that involve logarithmic functions. And some of you still are feeling a little uneasy with logs, and this will give you just some more practice with it to help you feel less intimidated by logarithms. Okay.
Logarithmic functions are often used to scale very large or very small numbers because they're easier to understand. So we look at 3 common models for logarithmic functions. The Richter scale determines magnitude for earthquakes. Find the pH of the solution and test the scale.
Okay, so last year around this time, I remember in terms of the decibel scale and noise intensity, there was a lot going on with football at this time of the year, as you well know. And I don't know if some of you realize or are familiar with it, but there were a couple of competing stadiums in the National Football League that were competing to get into like the Guinness World Book of Record for who can have the highest decibel levels. Anybody familiar with that? Any sports fans? Tio, do you know what the 2 cities were? Okay. Seattle, which is known as the Seattle Stadium, and Kansas, and they were going back and forth. And so I got really interested in this idea about how do they measure, you know, the decibel level? Is there a particular spot where they should be in the stadium to get, you know, the best measure of this decibel level? So students and I were drawing at the end of class pictures of stadiums, and one guy was he knew a lot about sound. I guess he worked in music, and we were discussing about how it bounces and where you would go, because they showed, I think it was in Seattle, they showed this guy at the end zone, and the crowd was there, and he's like, he's got the big, you know, the instrument that's measuring the sound, and he's like, come on, like this, and it was crazy. It's like this crazy thing. Anyway, this is just to show you like what math people think about, right? I can't even watch these football games without thinking about lecture and decibel scales. But anyway, so yeah, these are 3 common models now. I think, has anybody not heard of the Richter scale to measure earthquake intensity? Okay, and so that's a fairly common scale that's used. There's actually other scales that they use now to measure earthquake intensities, but this is really the most common and often what you would read sort of in the popular literature. pH, the idea of pH, whether something's acidic or basic, a solution has to do with the hydrogen ion concentration in a solution. And if you've had chemistry before, that might sound a little familiar to you. And the decibel scale, I think most of us are aware of different noise intensities. And decibel is measured with this little unit, D, little d. Come on, work. You're not going to work for me today? Oh, great. D, capital B. That's how we measure, that's a unit that we measure for decibels. Okay, so let's get going and do a couple of these problems. And so, Anna, you want to start us here with number 2 about earthquake magnitude? Yeah. Does anybody give me a number that they might be familiar with that you might read about in a newspaper or hear on the news or on the internet if they were reporting the magnitude of an earthquake? 7.5, yeah. Anybody else? 7.2. Anybody else? Has anybody ever heard of an earthquake of magnitude 10? 9? You've heard of one of 9? Chile in the 40s? Okay. Would they report one of 1? No, not really. I mean, it's not going to be that like great news, an earthquake of magnitude 1. But there were a couple of years ago here, or was it just last year? I was in my bedroom, and it was like the middle of the day, and I was like looking, and I swear I saw like the room go like this, and I'm like, wow, did I eat something funny? And then I found out later on that this area, Franklin County, actually experienced a small earthquake. And that was a really strange feeling. Has anybody ever been in an earthquake? Really? Whereabouts?
I used to live in California.
Oh, you used to live in California. Oh, yeah. So what was like the
worst? I slept through it.
You slept through it?
Yeah, but we had like, I think it was a
5.
5. Some stuff off the wall.
Yeah. Okay. Jennifer, what about you?
I was just here.
Oh, really? Yeah. Was that the one that I was just talking about like a year or so ago?
5th grade.
5th grade. Okay. So it wasn't a year ago. Was it strange?
Ordeal.
Yeah. Oh, half the day off. That's good. Mel, let's get one today. Coleman, what about you?
I was in China at the time.
Oh.
I was like 200 miles south of the big Sichuan hit.
Yeah.
And I was like, this feels weird. And like the news later, it's like, yeah, 200 miles north of here, this giant earthquake hit. And I was like,
oh, that's interesting. Okay. So yeah, so if you haven't experienced one, I think most of you are familiar with the numbers that report the intensity of earthquakes. And I just threw this in, I guess when I was developing this particular lecture a few years ago, I did some investigation about all this so I would know a little bit about what I was talking about. And this is just like a reading that I can't say it, seismologists might see that would be measuring the earthquake intensities. And there's something called S waves and all this sort of thing where they actually look at this particular instrument uses to measure these intensities. Okay, so let's take a look at the mathematics here. So the Richter scale defines the magnitude M of an earthquake, and that's measured by this particular equation, log of I divided by S. I is the intensity of the earthquake. Okay, and S is the intensity of a standard earthquake. It's like a constant that they use as a comparison. So we're comparing the magnitude by using division here. So we're comparing the intensity of the earthquake that's happening at a particular time to what we call the standard intensity of an earthquake. And this measures the smallest amount of earth movement. So this is like a constant. So here's 2 particular earthquakes that happened long before any of us were born. But this particular earthquake that happened in 1906 in San Francisco actually flattened the entire city and caused incredible fires and destruction. And it happened to have a magnitude of 8.3 on the Richter scale. Okay. Couple of years ago, there was an earthquake in Japan that happened near a nuclear reactor. Remember that one? And yeah, okay. Okay, so at the same time in Japan, an earthquake with magnitude of 4.9 caused only minor damage, okay? So this is at the same exact time. So you can imagine the earthquake wave, all right? So if I'm here in San Francisco, sort of emanating out towards, to the west to Japan. But by the time it hit Japan, it only caused minor damage. So here's a question, and this is what we want to get a sense of. Think about logarithms, common logs. This is a common log here because it's base 10. We don't put it in, but we know that it's base 10. So the idea here is everything is based on 10. Okay, so when we are trying to talk about how how much more intense would one earthquake be compared to another? Or when we see these numbers, 7 versus 5, what, to us, 7 and 5, they're only 2 units away from each other. But what does it mean when we're talking about the intensity of earthquakes? So I just want to give you a sense of that today before you leave. So maybe you'll hang on to something. Maybe not the mathematics of how we get this answer, but sort of what it means, these numbers, when you compare them. So if we want to compare these two earthquakes and try to figure out how many more times the one in San Francisco, how much more intense it was compared to the one in Japan, then what we do is we say, okay, we're going to measure the magnitude of the San Francisco earthquake, and that's equal to the log of I over S, and I'm just going to put the intensity of the San Francisco earthquake right there. That's what we're trying to, that's one of the pieces we're trying to solve for. And the other one would be the magnitude of the Japanese earthquake, which happened at the same time, and that would be measured by the Japanese intensity over this standard intensity, this reference value. So right now, all I can do is I can fill in what the magnitude of each of these earthquakes are, because that's given right here. The magnitude of the earthquake in San Francisco is 8.3. So I can fill that part in. And the magnitude of the one in Japan was 4.9. So I can fill that one in. All right, so what do I do from here? How could I take a look at solving this? Well, remember, this is a common log, so I could just take this log equation, which we don't really like working with, but we want to get at looking at these two values right here, and we have a log equation. And one of the little ways that we found to solve log equations was to perform an inverse operation, which was the exponential function. So we know that it's a lot nicer to look at an exponential equation if we can versus a log equation. So we can change this log equation to an exponential equation. It's equivalent exponential equation. And how can I do that? Don't let all this stuff here in parentheses mess you up, but how would I take that log equation and write it as an equivalent exponential equation? Well, I want to undo the log, so I don't want to introduce another log. I want to somehow write it as an exponential equation. So if I could take the natural log of both sides, but it's not going to undo any of this log stuff here. So how about if I gave you something like this? 8.3 equal the log of A. How would I write that as an exponential equation? 10. Why did he say 10? Because when we say log, we're really saying the common log, right? And we know the base is 10. We don't put that number in 10 because it's common. So we say, okay, this log has a base of 10. So the exponential equation that it's equivalent to must have a base of 10. We know any log, the answer to any log equation is the exponent. So 8.3 is the exponent for the base 10. And then your input for a log, your input into a log equation is your output for your exponential, because they're inverse functions. And remember, the inputs and outputs swap. So this would be how you would take this log equation and write it as an exponential equation, which is a lot easier to solve. Now I know what A is. It's 10 to the 8.3. So what I'm going to do now is I'm just going to take that same idea and apply it here. So 10 to the 8.3 is equal to this input right here into my log, which is the intensity of the San Francisco earthquake over the standard earthquake. And similarly, on the right-hand side here, 10 to the 4.9 is going to equal the intensity of the Japanese earthquake divided by S. So that's a proportion. I can do cross products, set cross products equal, or I could multiply both sides by S. The S's will cancel on the right side. And so I get S times 10 to the 8.3 is equal to the intensity of the San Francisco earthquake. And S, oops, that's supposed to be blue. S times 10 to the 4.9 is equal to the intensity of the Japanese earthquake. So remember, I was originally asking how many times more intense is the San Francisco earthquake compared to the Japanese earthquake? So we can measure that intensity through division. So really what I want to do is to say how many more times is the intensity of the San Francisco earthquake compared to the intensity of the Japanese? So if I now substitute what each of these things is equal to, I'll put that in the numerator, S times 10 to the 8.3 divided by S times 10 to the 4.9. Notice your S cancels out to 1. And here's your answer. 10 to the 8.3 divided by 10 to the 4.9. So how many more times intense is the San Francisco earthquake compared to the Japanese? What do I do to finish this off? I subtract my exponents, right? Yay, finally a use for exponent properties. There we go. And so it's 10 to the what? 3.5, 2.5, what's 2.4? What's 8.3 minus 4.9? 3.4. Okay. So you say, okay, so what does that mean? Well, 10 to the third would be, right? Is it 3.4? Did I do that right? Okay, everything's all right? All right, so 8.3 minus 10, 4.9, let's see what that is with our calculators. And I put some calculators on your table if you don't have one. So let's do 10 raised to the 3.4. 2,511 times, so approximately 2,500 times more intense. Well, that would certainly be one explanation for why there was so much more damage in San Francisco. All right. So let's take a look at this now. Increasing the magnitude by 1, say from 6 Richter scale value of 6 to 7 or 8 to 9, corresponds to increasing the earthquake intensity by a factor of 10. So every time you see a change of 1 in the Richter scale value, that means that the intensity is increasing by a factor of 10, and that makes sense since our common log has a base 10. Okay, so let's see if we can shortcut all this mathematics, because we're not going to go through this the whole time. Okay, every time we want to compare two earthquakes. So let's look at the final step here. What did we do here? So if I told you there was an earthquake, say in Chile, that had a magnitude of 8.2, and at the same time there was an earthquake, say in Mexico, that had a 5.6 reading, and I asked you how many more times it's kind of a funny thing to say, how many more times intense the earthquake was in Chile than the one in Mexico. You don't have to go through all of this. Can you tell from looking at the final sort of process of formula we used to shortcut this, to maybe come up with your own little model for comparing these two? 10 to the 2.6, and how did you get that? Yep, you subtracted 8.2 minus 5.6. So whenever you're trying to compare the intensities of two earthquakes, this is all you have to do, is subtract the two Richter scale values, and that becomes the exponent of 10. So in this case, it would be 10 to the 2.6, and let's see how many more times intense that is. 10, let's clear this out, 10 raised to the 2.6. There we go. 398, about approximately 400 times more intense. That just gives you a little bit of a feel for Richter scale values and thinking of those numbers and how they really measure the intensity of earthquakes. So if you see two values, you can compare them. I should have looked up the level that we experienced. I couldn't remember if it was a year or two ago in Greenfield to see how that measured. So any questions on this particular problem with the Richter scale before I move on? All right, let's take a look at pH scale. And I want to go to the internet real quick. I saw this great graphic last semester on Google. Right here, yeah, this was it. Which I thought was pretty interesting. Right here, this graphic. So this graphic measures the pH scale. And we say that 7 is neutral. A pH of 7 is neutral. Supposedly pure water, right? Pure water is neutral. And if you look at water, let me go to the sideboard. Water is, does anybody know the chemical formation for water, the chemical symbols? H2O, right? H2O. And what that means is you have one hydrogen ion and one hydroxide ion. And this plus and minus here for water neutralizes it. Okay? So what we're going to be measuring in when we look at pH is the hydrogen ion concentration. So if you have a surplus of hydrogen ions, like with acetic acid, which is CH300H, and what this looks like is this. You have carbon, and attached to carbon you have 3 hydrogen ion concentrations, and then you have O, and then your OH minus. So this hydrogen ion and this one neutralize each other. So you see with acetic acid, you have more hydrogen ion concentration than you do your hydroxide concentration. So that's what we're measuring from a chemistry standpoint, is how many, for acidic, is how many, like sort of a surplus of these hydrogen ions. So what I thought was really interesting about this scale is the lower your number, all right, the lower your number, excuse me, the higher your number, the scale's going down versus up. You have a pH of, say, 10 or 11. You're talking about things that are basic, what we call basic. Ammonia, lye. Some people think, oh, it's only these acids I have to worry about, but you can have damage done to you by very high things that have a very high pH level, as well as the acids like battery acid and stuff like that. So what I found really interesting is look at the normal range of stream water is between 6 and 7. So pure water is supposed to be neutral, 7, but the normal range of stream water is more acidic. Does anybody know why stream water is more acidic now? Why it would have a pH less than 7 and not be considered neutral? Anybody know? No? Has anybody heard of the term acid rain? Okay, so there's natural factors that affect the rain that falls down to the earth, like volcanoes and decaying vegetation, but most of the acidity in rain that's falling into our streams and lakes and forests and actually affect the animals and the stream, and the animals that live in the stream, the fish, is due to they say man-made, but people-made emissions from power plants. Most of the acidic rain comes from sulfur dioxide and nitric oxides, which are emitted by electrical plants that are burning fossil fuels. So when I was in graduate school, I was very interested in this idea. I happened to see one of the top 10 stories that's not reported, and I saw this thing called acid rain, and I was in a course then called environmental health. So I wanted to do some research on this. And anything that was, remember, we didn't have the internet back in those days. So anything written on this was all had to do with the Netherlands and what was happening in Europe. There was nothing happening in the United States except one little study in Worcester. This man was doing this one little study And I went to visit him and I was able to get his data and do this report. But it was like mind-boggling that nobody in the United States was reporting anything about acid rain. It was a problem over there. Well, now it's a problem everywhere. So keep your eye out. I mean, some of you probably heard about like the frogs that they've discovered in Minnesota that have multiple legs and no, is it? Yeah. You know, it's just, it's amazing. So anyway, there's a lot of stuff here that there's a lot of relationship between the stuff that happens in your everyday world that you might read about and some of this math, but you don't see the math. The math is hidden. So shampoo, who thinks about the pH of shampoo? Anybody think about the pH of shampoo? Every day, okay. Well, this morning I was using my shampoo. Okay, so if the pH is less than 7, which we call that acidic, and if the pH is greater than 7, we use the term basic. So let's find the pH of a shampoo if the hydrogen ion concentration is this number. Now, this is a very small number. It's 9.0009074. That's what this means here, 7.4 times 10 to the negative 10. So determine if shampoo is basic or alkaline. Does anybody have a sense of whether shampoo is basic or alkaline? Or, excuse me, basic or acidic? Some people say acid. Anybody else? Basic? Okay, well, let's see. Let's find the pH of shampoo. So all you do is you substitute this number for the hydrogen ion concentration. So let's do that. That's just a calculator exercise. We're going to take the log of 7.4 times 10 to the negative 10. So let's do that. Let's clear everything out. So I'm going to put 7.4 times 10 raised to the negative 10, Okay, that's my number. And now I'm going to take the log of that. So let me store that number in A. Store it in A. Okay. So now I'm going to say the opposite of the log of A. Let's recall alpha A. That way I get the whole thing. And there's my answer, 9.3. So what does that make it? Basic, right? It's basic. Okay, so this is just simply a plug-in and put it into your calculator type of exercise. Any question on this before we move along? So what's coming up next? These notes here. Oh, beer. Yay. Now you're talking my language here. Now, let's see. So red lager has a pH of 4.1. So what does that make it? It's acidic, right? Beer is acidic. So now we're asking if we have a pH of 4.1, what would be the hydrogen ion concentration? So let's use our formula and figure this out. Notice the hydrogen ion concentration has those little brackets on it. This is just the symbols they use in chemistry. I don't know why they do that, but that's what they do. So we're trying to solve for the hydrogen ion concentration. So the first thing I'm going to do whenever I try to solve any log equation is I want to isolate it. And right now it has a -1 multiplying it. That's the coefficient. So I'm going to divide both sides by -1. So I get -4.1 equals the log of the hydrogen concentration. Now, again, I just want to continue to try to hammer this home a little bit. Here's a picture of our log function. Our y-axis is our asymptote, and this just grows very, very slowly. We go through 1, 0, and we go through 10, 1. Remember, it's the inverse of the exponential function. And so if my log is a negative number, remember, this is your output, this is your y value. That means you have to be a number between 0 and 1. If your output, here's your log right here, here's your pH, I mean. If you're negative, you have to be a number between 0 and 1. Okay, good. It's going to be some small number here. All right, so let's find this. So, all right, we're back to the same question I asked you a minute ago. I need to solve this log problem. What exponential equation do I use to solve that log problem? What's the base of my exponential equation? 10, because it's a common log. 10. The answer to the log is the exponent. The output of my log is the input. So look, and for this particular, if I was writing an ordered pair for this log, a point on this graph for this log, my output is negative 4.1. My input, my x value, is the hydrogen ion concentration. Now, this is the log. Remember, your exponential function is its inverse. So you swap your domain and range. That's all you do. Your x's and your y. So in this particular case, the answer to my log becomes my exponent, because that's my input into my exponential equation. And my answer to this is my hydrogen ion concentration. So let's see what the hydrogen ion concentration would be for this lager if we know that its pH is 4.1. So let's take a look at that. Let's bring our calculator back up. Clear it out. So 10 raised to the negative 4.1 is equal to 7.943 times 10 to the negative 5. So that's approximately 0.00007943. Okay. That would be the hydrogen ion concentration. So that's how you work two different types of questions that have to do with pH level. If you know the hydrogen ion concentration, you just plop it right in, you throw it in your calculator, take the log, change the sign, there's your pH. If you know the pH, you throw that into the left-hand side of your equation and you change your log equation to an exponential equation, and then you just raise 10 to that power. Okay, yep.
Does it matter to what decimal?
No, not today. No, not for me.
Yeah. To the third.
I mean, you could leave it just like this, because this is exact as far as, I mean, this is as exact as we can get with our calculator here. That's okay. I just want to make sure you can basically get it, that's all. So you can see here, just like with the Richter scale, that if we increase our pH level by 1, that corresponds to decreasing the ion concentration by a factor of 10. Okay, because the smaller your ion concentration is, the more acidic you are. Is that right? The concentration. Yeah. It's been a long time since I've had chemistry, but I loved chemistry when I was in school. I know I'm weird. Okay. All right, I think we had one more for your activity. I don't have today's lecture notes. Oh, here they are. Do you have one more question to look at there? Do you have one more? Oh, no, just ends there, right? You don't have any other questions. Okay. Not for pH. Okay, so now we go on to decibel levels. And I was trying to find my lecture that had to do with the Seattle Stadium and the Kansas City Stadium, the football stadiums, and the decibel levels. I couldn't find it. And I didn't want to have to go back and, you know, do a Google search. But anyway, decibel level, the unit that we measured noise levels with is in honor of Alexander Graham Bell. Decibel. So this is the formula that we use to try to measure noise level. That's what the N stands for. Again, you see a log on the right-hand side, and you see this reference sound. This is acting just like the S did in the Richter scale problem. It's just the smallest, the faintest sound that we can measure with the human ear. Okay, so this is just some type of reference sound. So let's take a look at this. This is kind of an interesting thing. Average conversation levels, we are around 50 decibels, just to give you a sense of, you know, just the average conversation's about 50 decibels, okay? So if we were looking at a jet engine or a rock band, which we're going to look at in a few minutes, versus a bird, you know, out there chirping, this just gives you a sense of some kind of reference, frame of reference for this noise level. Okay, so again, it looks scary, but I hope by now we can see that these little formulas aren't that scary. The interesting thing here is that this quotient right here, I divided by I sub naught, has no units on it. Okay, so it gives the relative intensity of a sound, any sound, compared to this reference value. So let's see what this means. Suppose I divided by this I sub naught was 100. Let's calculate the noise level in decibels if we say that this ratio is 100. So all we do is we go back to our formula, and where we see I divided by I sub naught, we're going to just substitute in 100. And let's see what we would get for a decibel level there. So I divided by I sub naught is 100. And the common log of 100 is 2, because 10 squared is 100. So that would be a noise level, N would be 20. So we're talking about 20 decibels. So not as intense as a human conversation. So maybe someone's whispering really quietly. Right? So here's the same question that we have when we talk about the scales that we were just looking at with the pH scale and with the Richter scale. With the Richter scale, if we increased our magnitude by 1, that meant that the intensity of the earthquake increased by a factor of 10. So what happens if we now increase this by a factor of 10? So notice we were looking at this ratio as 100, and now we're increasing it by a factor of 10. How does the decibel level change? Let's do that real quick. N equals 10 times the log of 1,000. What's the log of 1,000? 3. So here you see similarly that increase of 1 that we saw with the Richter scale, but now that increase, oops, no log here. Now that increase, notice in both of these is being multiplied by 10. So now this gives us a decibel level of 30. So when we increase now by, when our intensity increases by 1 from 2 to 3, our decibel, our actual decibel, goes from 20 to 30. So let's see what the typical decibel level of a rock band is. Does anybody want to take a guess? So if human conversation is about 50 decibels. Any wild guesses about what you think the intensity of a rock band might be? 120. That's an interesting. 115. 70. Okay. Any other guesses? Doesn't hurt to guess, Alex. 300. Oh my God, I don't think you'd be hearing, but let's see. All right. All right, so now this number, again, this unit, watts per square meter, is how we measure the intensity. Okay, so this is the number that we put in where we see I. All right. So what is the decibel level of a typical rock band playing with an intensity of 10 to the negative 1? Well, what was I sub naught? I sub naught was right here, 10 to the negative 12 watts per square meter. So we now have the values for I, we now have the values for I sub naught. So it's just a little calculation. So N is equal to 10 times the log of I divided by I sub naught. 10 times the log, well, the intensity of the band is 10 to the negative 1. And the reference intensity here is 10 to the negative 12. Again, I use my exponent rules. 10, side note here, 10 to the negative 1 divided by 10 to the negative 12 is 10 to the negative 1, take away a negative 12, which is 10 to the 11th. 10 to the 11th. So log base 10 of 10 to the 11th. Remember, these bases are exactly the same here. So all I do is lift off my exponent and I get 11. So I get 10 times 11, which is 110 decibels. Boom, 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 boom. Well, I guess these two people right here are within 5. And without going over is usually the rule, right? So I think Tio wins this one. Was it Tio? All right, Tio. So it's 110 decibels. Okay, 110 decibels. So again, if we wanted to ask this question, the average perception of the sound intensity of a rock band is deafening. A decibel level of 110 causes ear pain. Okay, so if it was 300, you'd be, all right. So how many orders of magnitude, powers of 10, more intense is the sound of a rock band than the average conversation? Well, the rock band was 110, the average conversation was 50, so that's 60. So in terms of the number itself, it's 10 to the 6th more intense, which is what, 1 million times more intense than the average conversation. So that sort of finishes up our actual demo today of how we use logs, common log models for things that measure earthquakes, for measures noise, and measures the pH level. Your activity is on the next page. There's about 6 questions that has to do with stellar magnitude. How do we measure the brightness of stars? And you can work through this, and there's answers on the next page to check yourself. This will also give you a little bit of practice with using these log equations and log models.